Hello. So, welcome back to this series of lectures on numerical optimization. So, in the last class, we looked at convex sets and their properties. How do we characterize a convex set? So, in this class, we will discuss about convex functions and in general convex programming problems. So, we will first study about the convex functions and their properties and what are the nice properties of convex programming problems and what are the usefulness of convex functions. So, let us look at this two functions which are shown here. So, on the left side you will see a function which is nice quadratic function, and the function increases when x increases or x decreases. Now, on the right side you will see a function with lots of peaks and lots of valleys. Now, on the left side, if you see the function, if you take this point which happens to be a local minimum of the function, because in the neighborhood the function is increasing. Now, you will see that if as x increases the function value also increases, or as x decreases the function value also increases. So, this also turns out to be a global minimum. Now, that is not the case in the case of this function. For example, these points, as we saw earlier, these are all local minima. Now, among all these local minima, this is the point at which the function attains the least value, assuming that the function increases as x increases in this way or x decreases in the other way. So, you will see that this function is very nice function. It has a local minimum which is also a global minimum. Now, what are the properties of such functions? So, let us quickly look at this function. So, the function which we are considering, they are of this type. Now, so what are some important properties of such functions? Now, if I take any 2 points on this graph of the function and draw a line segment joining that graph, now you will see that the value of the function always is less than the point on this chord. Okay, so, the function always lies on or below this chord. So, suppose if we take a function like this, okay, and then suppose we take a chord joining any 2 points, you will see that the function always lies below this chord. Now, it may so happen that if you take these 2 points and then take a chord joining them, then you will see that the function is the value of the function is equal to the same value as is obtained using the chord. So, you will see that in this case the function always lies. So, if you take any point on the line segment joining these two, the value of the function will always be less than the value here, the value obtained here. Here also it is similar, and here if you take any point, the value of the function will always be on the chord. Okay. So, such functions are called convex functions, and good thing about such functions is that they have a local minimum which is also a global minimum. Okay. So, we will now formally see the definition of convex functions. So, let us consider a convex set C and a function f from C to R, a real valued function defined on the set C which is convex, is said to be convex. The function is said to be convex. If you take any 2 points x1 and x2 belonging to the set C, and any lambda which is a scalar in the closed interval 0 to 1, then the value of the function at any point on the line segment joining x1 and x2 in the set C will always be less than or equal to the value of the function interpolated between the 2 chords. So, let us look at the example again. So, if we define this function to be on this interval a to b, the closed interval a to b. Now, at this point what we have the value of the, so this is our function f of x. So, at this point we have a, the coordinates are a f of a, and at this point the coordinates are b f of b. Now, if you take any point on this line segment joining a and b. So, suppose let us take a point C. Now, now if you take the value of the function at C. So, this is C comma f c. So, you will see that if you now take a line segment joining a f a and b f b and interpolate the intermediate points, then you will see that f c, the value of the function will always be less than or equal to the value represented by the corresponding point on the chord. We just have to interpolate the function values using this line segment. Now, similar is the case here, and you will see that if we take these 2 points, so let us call them as E and H. Now, if we take a point here, so you will see that the value of the function is equal to the value obtained by using the interpolation of the points E f e and H f h. So, either the function value is less than the value attained by a point on the chord, or it is in this case equal to the point the value attained by a point on the chord. So, this is a convex function. Now, so what does this definition says that if you take any 2 points x1, x2 in the set C and take a lambda in the closed interval 0 to 1. So, get any point on the line segment joining x1, x2. So, lambda x1 plus 1 minus lambda x2, as we have seen earlier, if lambda is in the closed interval 0 to 1, it represents a point on the set on the line segment joining x1 and x2. And what the convexity says is that the function is convex if f of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda f of x1 plus 1 minus lambda f of x2. Now, so here is an example of a convex function. So, we take 2 points x1 and x2, take a chord joining the 2 points. Now, at any intermediate point on the line segment joining x1 and x2, the value of the function is less than the value obtained by interpolating the endpoints of the chord, finding the appropriate value on this chord of the function. Now, a function is strictly convex if this inequality is strict for any 2 distinct x1 and x2 in the set C and lambda is in the open interval 0 to 1. So, if this inequality is strict, then the function is said to be strictly convex. So, now, so if you look at our old figures, so you will see that this function is strictly convex, while this function is not strictly convex, because there do exist some points where the equality does not hold, the inequality does not hold strictly. So, the equality holds in that definition. So, that is why this function is not strictly convex, while this function is strictly convex. Now, if we consider a function which is of this type, so such functions are called concave functions. Or in other words, if we take the negative of this function, so if suppose this is minus f, this is f, and if we take minus f, so then so if this is our function f of x, and if we take a negative of this function, So, if we take a negative of the function which is minus f. Now, minus f is a convex function. So, if f is said to be concave if minus f is convex. So, there would exist some functions which are neither convex nor concave. For example, if we draw a function which is like this. Now, you will see that this is not a convex function, because if you take any 2 points on the function, on the graph of the function, and then take a chord joining them, you will see that in some regions the function lies above this chord, and in some regions the function lies below this chord. So, even if you take a minus of this function, that also will have the similar property. So, such functions are neither convex nor concave. Okay. So, now let us look at some examples. So, this is a function in 2 variables. So, you will see that it has a nice surface, the cup shaped surface, and such a function is a convex function, because if you take any 2 points on the graph of this function and take a chord joining those 2 points, that chord always lies either on or above the function. In fact, in this case the function is strictly convex. Now, as I mentioned earlier that if you take a function f on a convex set C, and that function is said to be concave if and only if the minus f is convex, and if it is said to be strictly concave if and only if minus f is strictly convex. So, here is an example of a concave function, and here is an example of a function which is neither convex nor concave. Now, you will see one more example here shown which is neither convex nor concave. So, you will see that if the variable x1 is greater than 0, then the function is concave. If the variable x1 is less than 0, then the function is convex. But if we retain x1 to be belonging to the set of real numbers, then this function is neither convex nor concave. Now, let us look at some examples of functions and try to identify whether they are convex or not by drawing their graphs. So, here we have a function f x equal to a to the power x, a transpose x plus b. Now, if we draw the plot of this function, so we have already seen that f x equal to a transpose x plus b will be a function like this, where a is a normal to the hyperplane. So, it is a hyperplane. Now, if we take any 2 points on this hyperplane and take a line segment joining them, we will see that it always lies on the function. So, f x equal to a transpose x plus b is a affine function which is convex. Now, you will see that this also satisfies the definition of a concave function, because minus f, if we take minus f, that also is a convex function. So, in fact, this is the only function, the affine function is the only function which is both convex and concave. Now, let us look at so this function is both convex and concave on Rn. Now, let us look at another function e to the power ax, where a is a real number. Now, if we look at the graph of the function, so we have x and f of x, and we want to draw the graph of the function, say e to the power x. So, this graph would look something like this. Now, if we take any 2 points on the chord of the function and join them, you will see that the function is always below the chord. So, in fact, this function is strictly convex. Now, if we take e to the power minus x, so suppose if we take a function f x to be f of x equal to e to the power minus x. So, this function would look like this, and if we take any 2 points on the function, on the plot of the function, you will see that the line segment joining those two always lies above the function. So, this is a strictly convex function. Okay, now let us look at some more examples. So, e to the power x is convex on R for any a in the from the set of real numbers. Now, the function f x is equal to log x. So, this function, now if you try to draw the graph of this function, so you have so f of x so this is the function that we are going to plot. F of x is equal to log x. Now, this function will look something like this. Now, if we take any 2 points on this graph of the function and draw a line segment joining those two, you will say that the function always in between these two line segments, in between these 2 points, the function always lies above this chord joining the 2 points. So, in this case, the function is concave. In fact, it is a strictly concave function. So, let us look at some other examples. So, f x equal to log x is a case of a concave function on the set of positive real numbers. Now, if we take the function x equal to x cube, and if we try to draw the graph of the function, so you will see that the function is somewhat like this, and you will see that now if you take any 2 points on the graph of the function and take a line segment joining those two, you will see that this function is neither convex nor concave. But suppose if we restrict ourselves only to the set of non-negative real numbers, so the domain of the function, if you restrict to the set of non-negative real numbers, then you will see that the function is convex. So, this function f of x equal to x cube is neither convex nor concave on the set of real numbers. Now, f x equal to mod x. So, let us look at how this function looks like. So, this is f x equal to mod x. So, you will see that if you take any 2 points on the graph of this function, the line segment joining them always lies on or above the function. Right. So, this function is a convex function. So, this shows that convex functions need not be differentiable. This is a continuous function. Now, one can also have some examples where the convex functions need not be continuous. But remember that convex functions have to be continuous in the interior of the domain, but there could be discontinuities at the boundary points. So, these are some examples of convex functions. You can always generate more examples of convex functions from the known convex functions. So, obviously, the next question that would arise is that how do we characterize a convex function? Given a function, how do we find out whether the function is convex? So, instead of trying to find out whether if we take any 2 points on the in the domain of the function and take a chord on the graph of the function joining 2 points x f x 1 and x 1 f x 1 and x 2 f x 2 and trying to find out whether the chord lies below the function or above the function. Instead of that, can we have a better way of characterizing a convex function? Now, before we go into those details, let us try to see why do we worry so much about convex functions. Now, the convex functions play a very important role in optimization literature, and as I mentioned that they have some nice properties, and we will try to see some of those properties of convex functions. So, let us consider a constrained optimization problem where x is any subset of Rn and f is a function from x to R, and consider this problem where we want to minimize f of x subject to the constraint that x belongs to the set x. So, this is a general constrained optimization problem. Now, we know that there exist 2 types of minima, one is called a global minimum and one is called a local minimum. Now, a global minimum is a point x star belonging to x such that the value of the function at x star is at least the value of the function at every other point in the domain. So, for any x belonging to the set x, f of x star has to be less than or equal to f of x, and then we said that x star is a global minimum of f over x. Now, as we saw earlier that it is very difficult to characterize a global minimum, because to check whether a point is a global minimum, we need the knowledge of all the points in the set, and then we need the knowledge of f of x for every point in the set x. Only then we can characterize whether a point is a point x star is a global minimum or not. So, we also use the definition of a local minimum. So, point x star is said to be a local minimum of f over x. So, if there exists a delta neighborhood of x bar such that in the delta neighborhood, so this b x bar comma delta is a delta neighborhood of x bar, and that we take an intersection with respect to the set x, because we always want we are always worried about the feasible points. So, if we collect all that feasible points in the delta neighborhood of x bar, then if the value of the function at x bar is at least the value of the function at all the other points in the feasible neighborhood, delta neighborhood of x bar, then we say that x bar is a local minimum. Now, the good thing about the convex function is that if f is a convex function and x is a convex set, then every local minimum of this problem is a global minimum. So, in other words, we do not have to worry about finding out different local minima for a convex programming problem, where the function is convex, the objective function to be minimized is convex, and the constraint set is a convex set. Now, such problems are called convex programming problems. So, let us formally define convex programming problems. So, let C be a non-empty convex set in Rn, and f be a function from C to R, and let f also be a convex function. And now, what we are interested in is solving a problem where we want to minimize f of x subject to the constraint that x belongs to C. So, when f is a convex function which we want to minimize and the constraint set is also a convex, then it is called a convex programming problem. Now, suppose f is a concave function and we want to maximize a concave function over a convex set. That also is a convex programming problem, because maximization of a convex function can also be written as a minimization of a maximization of a concave function can be written as minimization of a convex function. So, if a problem is of this type, where we want to minimize a convex function over a convex set, this is called a convex programming problem. And the important property of this convex programming problem is that every local minimum of a convex programming problem is a global minimum. So, we really do not have to worry about the problem of local minima as far as convex programming problems are concerned. So, these convex programming problems have lots of interesting applications in different areas of mathematics, engineering, science and so on. So, these problems are very important, and we should know some of the important properties of convex programming problems. And one of the properties is that every local minimum is of a convex programming problem is a global minimum. So, let us now try to prove this property of convex programming problem. Now, if the constant set C is a singleton set, then the theorem is obviously true, because there is only one point in the constant set, and that point will always be a global minimum. So, the theorem is trivially true in such a case. Now, so let us assume that there exists some x star belonging to C, which is a local minimum of f over C. So, by the definition of a local minimum, what we have is that there exists a delta neighborhood of x star, such that f of x star is less than or equal to f of x for all x in the region of C intersection the delta neighborhood of x star. So, the delta neighborhood of x star is shown here. Now, let us call this as a set S. Now, what we want to do is that by the definition of a local minimum, it is true that x star is a local mean in the delta neighborhood, delta feasible neighborhood around x star. Now, what we want to show is that f of x star is also a minimum function value that can be attained over all x belong to C. Now, we have shown that by the definition of local minimum, it is the minimum in this region, but what about the remaining region, that is the region which is shown by the green color here. So, if you can show that f of x star is less than or equal to f of x for any x in this region, the remaining region, then we can conclude that x star is indeed a global minimum. And let us see now how to do that. So, let us call this region the feasible delta neighborhood around x star. Let us denote it by the set S. So, S is basically the intersection of C and the delta neighborhood of x star. Now, what we need to show is that f of x star is less than or equal to f of x for all x in the set C which are not in the set S. So, the green color region is what we are interested in. So, if you take any x in that region, we want to show that f of x star is less than or equal to f of x. But we already know that f of x star is less than or equal to f of x for all x belongs to S. So, let us consider a point in the delta neighborhood of x star, and let us call that point as the point y, and y is not equal to x star. Now, what we do is that we take a line segment joining x star and y and extend it to some point x in the region C minus S. So, consider a point x on the line segment joining x star and y, and x belongs to the set S, C minus S. Now, we want to see what can we say about f of x star and f of x, and our aim is to show that f of x star has to be less than or equal to f of x. So, let us see how to do that. Now, note that the set C is convex. So, x star is in the set C, x is in the set C. So, any line segment joining x star and x always lies in the set C. So, let us take any point y on the line segment joining x star and x. Let us exclude the points x star and x and take any point on that open line segment joining x star and x. Now, we know that f of x star is less than or equal to f of y. This is because y is chosen to be in the set S, and by 1 f of x star is less than or equal to f of x for all x belongs to S. So, clearly f of x star is less than or equal to f of y. Now, this y we can write it as lambda x star plus 1 minus lambda x. So far we have used the convexity of the set C. Now, we can use the convexity of the function f. Now, since f is convex, we take any x star and x in the domain, take a line segment joining those two. So, by the definition of convexity, f of lambda x star plus 1 minus lambda x is less than or equal to lambda f x star plus 1 minus lambda f x, because f is convex. Now, remember that lambda is in the closed interval 0 to 1. So, if you rearrange this, what we get is that on the left side 1 minus lambda f x star is less than or equal to 1 minus lambda f x for all lambda in the open interval 0 to 1. Now, if we divide throughout by 1 minus lambda, what we get is f of x star less than or equal to f x for all x in the set C minus S. So, for all the points in the set C which are not in the set S, that is the points which are shown in the figure by green color, we have shown that f of x star is less than or equal to f of x for all those points in the set C minus S. And by the definition of local minimum, f of x star was always less than or equal to f of x for x belongs to S. So, if we combine 1 and 2, we will see that f of x star is less than or equal to f of x for all x belongs to C, and which means that x star is indeed a global minimum of f over C. Okay. So this is an important theorem which says that for every convex programming problem, a local minimum is a global minimum. So, the next question that we would like to ask is that suppose a convex programming problem has multiple local minima which also are now global minima because of this theorem. How are they positioned in the set in the convex set C? In other words, in a common terminology, we ask the following question: are those global minima of a convex function scattered at different places in the set C, or they always are combined together? So, we will try to answer this question. So, this is another important theorem in the theory of convex programming, and the theorem states that if you collect the set of all optimal solutions to the convex programming problem, then the set of all those optimal solutions is a convex set. So that theorem essentially tells us that the global minima of a convex programming problem, if they are not scattered everywhere, but they always try to form a convex set. So, we will see how to prove this. Now, if the set C is a convex set, and if we get a unique optimal solution, then that set is always convex, because we know that any singleton set is a convex set. So, if we have only a unique solution, then the theorem is trivially true. So, there is nothing to prove there. So, let us try to prove in the case where we have multiple global minima. So, let us take all those global minima and put them in the set S. So, S is the set of all the points in the set C such that the fz is less than or equal to fx for all x belongs to C. So, this S is the set of all global minima of a convex programming problem. Remember that the function f is convex and the set C is also convex, and we are trying to minimize the objective function f of x, which is a convex. So, hence the problem is the convex programming problem. Now, what we have to do is that we have to show that the set S is a convex set. Now, to show that any set is a convex set, what we have to do is that we have to take 2 points, any 2 points in the set S, and show that the line segment joining those 2 points entirely lies within the set. So, if you can show that, then the set S becomes a convex set. So, for that purpose, what we do is that let us take 2 points x1 and x2 in the set S, and obviously we take the points which are distinct, and then take a line segment joining these 2 points. Now, since x1 and x2 belong to set S, and we know that every local minimum of a convex programming problem is a global minimum. So, we have f of x1 and f of x2 to be equal. So, since they belong to the set S, we can also say that f of x1 is less than or equal to f of x, and f of x2 less than or equal to f of x for all x belong to C, because both x1 and x2 belong to the set S. Now, since C is a convex set and x1 and x2 are any 2 points in that convex set, we can say that by the definition of a convexity of a set, we can say that lambda x1 plus 1 minus lambda x2 that always belongs to the set S, set C for all lambda in the closed interval 0 to 1. Now, we can use the convexity of the function. So, how do we use the convexity of the function? So, since f is convex, we can write f of lambda x1 plus 1 minus lambda x2 to be less than or equal to lambda f x1 plus 1 minus lambda f x2. This is by the definition of convexity of a function. Now, you will see that f of x1 is less than or equal to f of x, and f of x2 is also less than or equal to f of x. So, this the quantity on the left side is less than or equal to f of x2. So, which is shown here. So, what does this mean? So, this means that f of lambda x1 plus 1 minus lambda x2 is less than or equal to f of x2. Now, this inequality cannot hold, because in that case what will happen is that will contradict the fact that f of x2 is less than or equal to f of x for all x belong to C. So, it will contradict that. So, this has to hold with equality. Now, what does that mean? That means that lambda x1 plus 1 minus lambda x2 also belongs to the set S for all lambda in the range 0 to 1, and therefore, this implies that the set S is a convex set. Okay, so we have studied 2 important properties of a convex programming problem. The first property is that every local minimum of a convex programming problem is a global minimum, and not only that, but the set of all global minima of a convex programming problem is a convex set. Now, given these 2 important results, now we will start studying more about convex functions. Now, one of the things that we would like to study is that how do we characterize a convex function. Okay. Now, to characterize a convex function, there is a nice way. So, let us define a function f from x to r and describe it the function by its graph. So, this graph is a subset in the n plus 1 dimensional space, and it consists of the points x and x comma f x, where x belongs to the domain of the function. Now, suppose if we describe the function by its graph like this, then the epigraph of a function is a subset of Rn plus 1, and is defined as the set of all points x y in the n plus 1 dimensional space, so that x belongs to x and y is a real number and y is greater than or equal to f of x. So, if you take a function, so this is the function, this is the graph of the function. So, as I said, the graph is a set of all points x comma f x. So, this is the graph, and the epigraph of the function is a set of points which are on or above the function. So, you will see that this is an unbounded set, all the points for which y is greater than or equal to f of x, all the x comma y where y is greater than or equal to f of x. So, the points on the curve as well as the points above the curve. So, this is called the epigraph of the function f. So, if we take a function which is like this, then if we consider all the points which are on or above the function, so this turns out to be the epigraph of this function f. So, these are some examples of the epigraph of a function. Now, along similar lines, one can also define so if we take the points which are below the function, then that is called the hypograph of the function. So, similarly, here we can draw the hypograph to be like this. So, this is a hypograph of the function. So, the points which are on or above the function, they constitute the epigraph of the function, and the points which are on or below the function, they constitute the hypograph of a function. So, we can see some examples here. So, here I have drawn a subset of the epigraph, because the epigraph is typically not a bounded set. So, I have just drawn a subset of that epigraph. Actually, you will see that all the points y such that y greater than or equal to, all the points x y such that y greater than or equal to f of x. So, you will get all the points even above this, but for convenience I have just drawn the subset of the epigraph in these figures. Now, there are three different functions shown here, and if we look at the epigraphs of these three different functions, and if you especially if you look at the epigraph of this function, you will see that this function is convex and the epigraph of the function is a convex set. Now, that is not true in these two cases. So, if you take a line segment joining 2 points in the epigraph of the set, you will see that the entire line segment does not belong to the epigraph of the set. While if we take a line segment joining any 2 points in the epigraph of this function, then you will see that the line segment entirely lies within the set. So, that means that if we have a convex function, then the epigraph of the function is a convex set, and if we do not have a convex function, the epigraph of a function is not a convex set. So, now let us try to give a formal theorem. So, suppose we have a set C, which is a convex set, and a function defined on the set C, a real valued function defined on the set C, then F is convex if and only if the epigraph of F is a convex set. We will try to prove this. So, let us assume that the function is convex. Remember that we have to give the proof in two parts. The first part is that we assume that F is convex and show that epigraph of F is a convex set, and the other part is that assume that epigraph of F is a convex set and show that the function is convex. So, let us first prove the part where we assume that the F is function F is convex and prove that epigraph of that function is a convex set. Now, to prove that epigraph of a function is a convex set, what we need to do is that we take 2 points in the epigraph of the function and then show that the line segment joining those 2 points belongs to the epigraph of the set. So, let us see how to do that. So, let us take 2 points x1, y1 and x2, y2 in the epigraph. Now, since these 2 points belong to the epigraph of the function, we know that by definition of the epigraph of a function, y1 is greater than or equal to f of x1 and y2 greater than or equal to f of x2. Now, we take a we use the convexity of the function. So, if we take any lambda in the closed interval 0 to 1, because f is convex, that is what we have assumed, f of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda f x1 plus 1 minus lambda f x2. Now, we know that f of x1 is less than or equal to y1, f of x2 less than or equal to y2. So, the right side is less than or equal to lambda y1 plus 1 minus lambda y2. Now, what does this mean? So, we have a point lambda x1 plus 1 minus lambda x2 which belongs to the set C, such that f of the function value at that point is less than or equal to some real number. So, which means that the point lambda x1 plus 1 minus lambda x2 comma lambda y1 plus 1 minus lambda y2 does belong to the epigraph of the function by the definition of epigraph. So, what we have therefore is that the point lambda x1 plus 1 minus lambda x2, lambda y1 plus 1 minus lambda y2 belongs to the epigraph of F. So, which means that the epigraph of F is a convex set, because this holds for all lambda in the range in the closed interval 0 to 1 and for any x1, y1 and x2, y2 belong to the epigraph of F. So, we have taken 2 points in the epigraph and shown that for any 2 points in the epigraph, the line segment joining the 2 points always lies in the epigraph of the set, which means that the epigraph of F is a convex set. Now, we will prove the other part. So, let us assume that epigraph of F is a convex set, and then we have to show that F is a convex function. Now, so to show that F is a convex function, we have to show that it satisfies the definition of convexity of a function. Now, since epigraph is a convex set, let us take 2 points in the set C and let us consider 2 points on the epigraph. So, these are the 2 points actually on the graph of the function, and the points on the graph also happen to be the points in the epigraph as well as the hypograph. So, x1 fx1 and x2 fx2 always belong to epigraph of F. Now, we have assumed that epigraph of F is a convex set. So, the line segment joining any 2 points in the epigraph always belongs to the set. So, by this we can say that lambda x1 plus 1 minus lambda x2 and lambda fx1 plus 1 minus lambda fx2 always belongs to the epigraph of F for any lambda in the closed interval 0 to 1. Now, by the definition of epigraph, so what we have is that since this point belongs to the epigraph, what we have is lambda fx1 plus 1 minus lambda fx2 greater than or equal to f of lambda x1 plus 1 minus lambda fx2. So, this value, which is a real number, is greater than or equal to the value of the function at the point lambda x1 plus 1 minus lambda x2 for any lambda in the closed interval 0 to 1, and therefore, this function is convex. So, what we have shown is that the function f defined on a convex set C, a real valued function defined on a convex set C is convex if and only if the epigraph of the function is convex. Now, if we look at some other function, so let us consider the function which is mod x, and then let us try to draw the epigraph of this function. So, you will see that epigraph of this function is a convex set. Now, one good thing about this characterization of epigraph, this characterization of convex function is that the function need not be differentiable. So, even if the function is not differentiable, we can always find out whether find out its epigraph and check whether it is a convex set and find out whether the function is convex or not. But if the function is differentiable, it's analytically easy to characterize a convex function. Now, before we look into the differentiable look at the differentiable convex functions, let us look at what are called the level sets. So, let us consider a convex subset of Rn and a real valued function defined on the convex set C. Now, the level set of f for a given alpha is determined as the set of all points in the set C such that f of x is less than or equal to alpha, where alpha is a real number. So, since this set depends on alpha, we show the dependence of that set in the definition of the level set. So, when we say C alpha, what we are interested in the set of all x in the set C such that f of x less than or equal to alpha. Now, we have a theorem which says that if f is a convex function, then the level set C alpha is a convex set for every alpha belonging to R. Now, it is easy to prove this theorem. So, suppose that we take any 2 points in the C alpha set, and what we have to show is that if f is a convex function, then C alpha is a convex set. So, we have assumed that f is a convex function. So, and we have defined C alpha to be this way. Remember that while defining the level set, we do not need f to be a convex function. Now, x y belong to C and f x less than or equal to alpha and f y less than or equal to alpha. That is by the definition of C alpha, because since x y belongs to C alpha, they clearly belong to C, and f of x and f of y both are less than or equal to f of alpha. Now, let us assume that f is a convex function. So, we take a point z which is on the line segment joining x and y. So, x and y belong to C as well as C alpha. So, this line segment also belongs to both. So, clearly z belongs to, so any point on that line segment joining x and y belongs to the set C. Now, we assume that f is convex, and by the definition of convexity of a function, f z is less than or equal to lambda f x plus 1 minus lambda f y. And since f of x is less than or equal to alpha, f of y less than or equal to alpha, what we have is f z less than or equal to alpha. So, for any line segment joining x y in C alpha, we get any point z on that line segment also lies in the set C alpha. So, which means that C alpha is a convex set. So, if we have a convex function f, then the level set C alpha is a convex set. So, this is an important property which will be used to generate more convex sets from a convex set from convex functions, and we will see that sometime later. But remember that the converse of this theorem is not true. So, if every level set C alpha of a function is a convex set, that does not mean that the function is a convex function. So, I leave it as an exercise to you to find out the functions for which the level sets are convex, but the function is not convex. So far we have talked about the convex functions and used epigraph to characterize the convex function. Now, suppose the functions are also differentiable, then how do we characterize them to be convex functions, and if they are twice differentiable, then how do we characterize them to be convex functions. So, we will study those things in the next class. Thank you.